What I want to do here is use the fake data example we came up with to see what happens when we employ mean imputation as our missing data strategy. So the top left here still has the complete data. And now we're looking at the top right where the data was missing completely at random. So recall, the black points here are just a subset, a random subset of the black points here, as if we drop some of them in a puddle randomly. So we're going to impute the missing education values using the mean of education. So the mean of education was just a little over 14. Okay, that's what it was. It's looking at all the education values here. And you know what? If we look at the missing completely random data, the mean observed education value was also right around 14, as it should have been. Okay, so we calculate the mean of the not missing education values in this data set. And then for each of the people who was missing education, we guess that their education level is exactly equal to the average education value. Now remember, we said that the ages are not missing, right? That's the assumption we're making. So this person here, we perhaps know that person is 13 years old, so we're going to plot a point with age equals 13 and education equals exactly to the average education value that we observed. Okay, so now we have these dots filled in. So a good thing here is that we now can actually plot all the data points. We can see, the full distribution of ages. That's good, right? We're not missing any people now. Another good thing is that if we use this filled-in data set to try to calculate the mean education, we get a reasonable value. But there's a couple things that don't work so well. So one thing that doesn't work so well is we've lost the relationship between age and education that used to exist in the original data set, right? We can't see that with this missing data strategy of mean imputation. And also, we have a variance problem. So if you were to look only at education, there'd be a big peak at this value, right? There'd be a lot of people whose education values were exactly whatever that is, 14.5, right? Too many. And so the variance of the education values is now too small because too many of the points have education values exactly equal to the mean. Remember, the variance is the average square distance from the mean. So if a lot of points are right at the mean, the variance goes down. So although filling in the missing education values with mean imputation for the missing completely at random data set allows us to have a good estimate of the mean education, it gives us an underestimate of the variance of the education value variable when we do that. Now let's look at the missing at random data set. It's the same thing. So we knew the ages of the people who were missing their education values. And now we've guessed that those people's education values are equal to the average education value observed in this data set, which was a little lower, maybe closer to 13 in this data set. Why is a little bit lower? Because we didn't have some of the higher education values up here. So the mean was now a little lower, more like 13. And we've made this guess, okay? So this is not as good as in the previous case, right? Because if we were to take the mean education, it would still be equal to the same mean education we had before imputing, which is not ideal because it's missing some of, again, the higher values. We have lost the relationship between age and education, and we continue to have a variance problem. Right, we continue to have a variance problem. So really the only thing what we've seen so far that mean imputation does excellently is it maintains a good estimate of the mean in the missing completely at random case. Right, that's all it does here. If we have data that's missing not at random, this is really not so good, right? Because remember, we cut off anybody with an education value above 13 here, which means that the average education value observed in this data set is more like 9. So for any person whose education was missing in this data set, we just filled in a 9, which means when we take the average education value in this data set, we'll just continue to get the wrong answer, right? This is really not going to work very well. The variance will continue to be way too small. In fact, it'll get even smaller now that we've imputed 9 for all these people. And we never did have the relationship between age and education, and we certainly haven't been able to recover it using mean imputation. So what is mean imputation good for? Again, it is good for a case where your main goal is to create a data set that maintains a good estimate of the mean and you think you have missing completely at random data. But it's also useful sometimes if there's only 1 or 2 missing values for just a couple of the variables. In other words, a situation where there's very minimal missingness in your data, a huge data set with just a couple cells missing, and you just need to be able to publish that data set or run an analysis on it. In those cases, it can be simple to just stick the means of the variables in there and perhaps would not have big consequences if it's only a couple cells in a large data set. But more generally, we want to do a little bit better than mean imputation. Now, our biggest complaint here, or our first complaint here, is about this variance issue, right? The idea is that even in the missing completely at random case, when I filled in the means, I maintained the mean education, but I've made the variance way too small. So the next slide shows one of the things that we can do about that. So this idea is imputing by drawing from observed values. What does that mean? So again, we start with our complete data that shows age and education for all of the data points. What are we going to do here for missing completely at random? For each person who was missing education, remember we know their age, right? So there's this 13-year-old over here whose education's missing. Now, instead of guessing that every single person's missing education is actually equal to the average observed education, I'm going to take each person who's missing education, randomly draw from the people who are not missing education, and use that drawn person's education to fill in the missing person's education. In other words, imagine a big bucket full of all the people whose education values are observed. Anytime I want to impute or guess at a missing education value, I stick my hand into that bucket, draw one person, and use that person's education to fill in the missing one. Then I put that one person back in the bucket again. So for example, you can see that this person, this 13-year-old, has their education imputed based on drawing this person right next to them. That just happened to be what happened. Okay, so I guess that this person's education was about 7 or 8, right? Based on drawing this number from the hat, right? This person over here, right? This person over here whose age was about 18 was missing education. How did I fill it in? I stuck my hand in the hat and I happened to draw this education value. So that's the one I filled in. Okay, so that's how these red dots came about. So what are the pros and cons here? Well, we have continued to approximately maintain the mean. If my goal is to have a data set that has a good estimate of the mean of education, this works great, still working just fine. And we've made some progress. This approach also allows us to maintain the variance. If my goal is to learn about the variance of education, what is the range of education values for people in this data set, this approach maintains that. It allows me to get a good estimate of the range of education, right? If I were to take a data set in which somebody had used this imputation method and take the variance of education, I should get about the same number as I would if I had the original complete data set. So that's good. I'm still missing something, which is the relationship between age and education, right? That is not maintained here, right? It's really not realistic that this person who's 18 has as much education as this older person, or that this person who is actually the oldest one of the data set has this very low value of education, right? That's not realistic based on the relationship we see between age and education. Moving along to the missing at random data, we're going to use the same approach by drawing from the observed values. So imagine that I have, well, I do have the ages for each of the people who are missing education. I'm going to put all the observed education values in a bucket, draw from those to fill in the ones that were missing. Okay. So this is still not going to maintain the mean, and it's not going to maintain the variance, or not going to give me a good estimate of the original mean and variance of education, because we have this problem that we only have lower education values in general. We're missing most of the higher education values. So when we draw from the black dots in a bucket, we're just still not drawing frequently enough from the high values. And so we're going to have a little bit of an underestimate of the mean and also an underestimate of the variance here. But it's still better, right? The variance won't go down as much as it did when we had this ridiculous mean imputation where every single person of any age had exactly the same imputed education. At least now there's a little bit more variance to it. So it's an improvement, but for missing at random is not good enough. For missing at random, where the fact that an education value is missing is correlated with some other variable, it's really going to be important to maintain this relationship between education and age, between the missing variable and some other variable. So that's not quite good enough here. And then missing not at random, we continue to just fail terribly, right? So I'm going to take all of the black dots that we did observe, put them in a box, and then for each person whose education was missing, I'm going to draw from those values. The problem is I didn't actually have any education values over 13, so it's impossible to draw realistic education values for these people who are older. So if I have missing not at random, once again, this strategy does not work. Now, preview, missing not at random means that no strategy at all is going to work. Okay, missing at random means eventually we'll find something that works. And missing completely at random means that already we're finding a strategy that pretty much works. This strategy is fine if our goal is to learn about the mean and variance of education, or to create a data set that maintains good estimates of the mean and variance of education, rather than looking at the correlation between education and age, which is not maintained.